Hi Method students. In this video we're going to have a look at the normal distribution curve, but in a bit more detail. We're actually going to look at some what we call approximate confidence intervals that are associated with a normal distribution. You might have heard of this rule before, it might be brand new to you, but there's a rule that we call the 68, 95, 99.7% rule. And these percentages give us approximations for what percentage of values, or what percentage of a distribution occurs between certain values. So we're going to have a look at this in a couple of diagrams. It's very much a visual method, but you can see with this bell curve that's drawn here, what we've got is we've got the mean of the normal distribution marked along the x-axis here. Remember that for a normal distribution, the mean occurs where the peak of the curve is. And then we've got these markings. We've got 1, 2, 3 markings above the mean and 1, 2, 3 markings below the mean, and they're evenly spaced out. And what these markings are representing is the mean plus or minus a whole number multiple of the standard deviation. So what we have is that if you go from one standard deviation below the mean to one standard deviation above the mean, this rule approximates that you've got about 68% of the distribution between those two numbers. Okay, and you can see that each section is actually marked with 34% because together that gives you a total of 68%. Right, so remember that this is an approximation, but it's actually a very good approximation for the percentage of a distribution that is within one standard deviation of the mean. If we go from the mean to 2 standard deviations below and then 2 standard deviations above, we get about 95% of the distribution. Or another way of thinking of it is that about 95% of a distribution, 95% of a normal distribution is within 2 standard deviations of the mean. And if we go 3 standard deviations below the mean and 3 standard deviations above the mean, we've got about 99.7% of our distribution between those two values. So you can see that nearly all of the values in a normal distribution are within 3 standard deviations of the mean. It's very unusual for a value to be more than 3 standard deviations away from the mean in a normal distribution. Okay, another way to visualize that is to actually think of each of those rules kind of separately. So on the notes here, we've put, I guess, one version of the graph where all the percentages are written in there all in one, but you might find it more helpful to visualize them separately. So here's a normal distribution with the 68% rule, which is, one standard deviation either side of the mean, covering 68% of the distribution. And you can sort of see that as well. That means that on the outsides, we've got the remaining 32% shared symmetrically. Then we've got our 95% rule. So that's 2 standard deviations below the mean to 2 standard deviations above the mean, containing 95% of the distribution. And then our other 5% evenly shared on the outsides. And then our 99.7% rule with the 3 standard deviations below to 3 standard deviations above. Okay. This little note at the bottom here of this page just says that if we have a continuous random variable x and it's got a normal distribution, where the mean is, whatever the mean is, we represent it with mu, and the variance is sigma squared, that can be written using this notation here. So if you ever do see that notation, that's just indicating that you've got a normally distributed variable, and the first number is telling you the mean, the second number is telling you the variance. Remember that the standard deviation is the square root of the variance. Another key point as well that particularly comes up later, but it's good to understand straight away. When we're looking at these normal distributions, we're representing continuous variables. So things like weight or time or distance, not discrete variables, right? So these variables can take any value. They're not like a counted whole number value. These variables often can take any value. All right. So here's an example. We're told that grades from a physics test are normally distributed with a mean of 84 and a standard deviation of 4. Right, so maybe this is some sort of test where 84% is the average and the standard deviation is 4%. And this question is asking us to find the approximate probability that any particular grade, so if we just picked a student's grade at random, find the approximate probability that a particular grade would be between 80 and 88 or between 72 and 96 and so on. So what we do in a question like this is we actually sketch the bell curve, and I'm going to use just some separate paper here, just so I've got more room to kind of make the sketch nice and big, and that is a good rule of thumb to try to make the sketch pretty big. So what I'm going to do is I'm going to draw a bell curve with a mean of 84 and a standard deviation of 4. And so what we do, right now, you try to make your sketch as neat as possible, but it doesn't have to be perfect. So I'm going to mark on 84 as the mean, and then 1, 2, 3 evenly spaced sort of dashes above, and 1, 2, 3 below. Again, it doesn't have to be perfect, but the neater you can make it, the better. And remember that, so each of these is going to represent 1 standard deviation away from the mean. So each value is kind of 4 units higher than the previous one because the standard deviation is 4. Okay, so this is the distribution of, we could call this test scores as our x-axis variable. Okay, so the first question was to find the approximate probability that a particular grade would be between 80 and 88. So between 80 and 88, that's giving us, let's see if I can color code this to make it slightly easier to read. So 80 and 88, if we were to represent that on our bell curve, well, that is one standard deviation below the mean to one standard deviation above the mean. And remember that our rules say that between those two values, we should have 68% of the distribution. So we would expect 68% of the test scores in this question to be between 80 and 88. So the probability that a particular grade would be between 80 and 88 will just be 68% or 0.68. So we can write for question A, PR, 80 is less than 88. That probability would be equal to 0.68. Actually, I should probably say approximately equal to, because remember that these are approximations. So approximately equal to 0.68. Part B, the probability that we're between 72 and 96. Well, again, we just go back to our bell curve. We find 72 and 96. I'm just going to use a different color here. So, oops, there's 72, there's 96. You can see that that's 1, 2, 3 standard deviations below the mean and 1, 2, 3 standard deviations above the mean. And our rule says that when you go 3 standard deviations either side of the mean, that should give you 99.7% of the distribution. And so the probability there would be 99.7 or 0.997. All right, for question C, the probability that our test score is above 88, well, we go back to our bell curve again. Now, we already looked at between 80 to 88, and we saw that that was, because that's one standard deviation either side of the mean, there's 68% in the middle there. That means that the remaining 32% of the distribution, the remaining 32% of the scores would be on either side of this 68%. And because this normal distribution is symmetric, that 32% is divided evenly. And so there's actually 16% of scores which would be above 88. So that's just from 88 and above is 16%. So we could say that the probability of our variable being above 88, our test scores being above 88 would be, again, I should write approximately equal to 16% or 0.16. And lastly, probability that we're below 92, back to our bell curve. Now 92, one more color here. All right, so here's 92 along the x-axis. Now that's 1, 2 standard deviations above the mean. Right, so normally we would say, if we're talking about 2 standard deviations away from the mean, that in between, so in the middle here, from 76 to 92, we would have 95% of the distribution. And that also means that on the outside, we're left with the other 5%, which would be sort of here, and that would be 2.5%, and here, which would be 2.5%. So this question was just saying, we want it to be below 92 or from 92 and below. So really that's going to be the 95% that's in the middle here, plus this 2.5% at the end. So from 92 and below, I've made a real mess of my diagram here, so I'm just going to draw that, extend that up. From 92 and below all the way down, we've got 97.5% of the distribution. 97.5% of the scores are below 92. So again, to answer that question, we can write our 97.5% as 0.975. And it would be fine to write all these as percentages as well, but often with probabilities, it's more common that they're given as decimals. So that's just a bit of an example of using a normal distribution. And really the good rule of thumb there is to sketch your bell curve. Whenever you get a question like this, draw a quick sketch of the bell curve. Even a bad sketch will help you understand what's going on. Okay, next little section here is on standard scores. And a standard score, really, what it does in practice is it allows us to make reliable comparisons which take into account the mean and the standard deviation of a particular distribution. The previous example was about test scores. If you imagined, you know, that you did a test for, say, maths, and it was a really, really hard test, so the average mark was only like 50%, but then you did a test for English and it was actually quite an easy test and the average mark was 80%, well, it wouldn't really be fair to compare one mark to the other because the English mark should be higher because it was an easier test. So standardized scores kind of take into account what the average is and also what the standard deviation is, so that you can kind of make more fair and reliable comparisons. And a standard value, which is sometimes called a standard score, or sometimes a Z score, we use the lowercase z here to represent it, is a way of calculating a value that just gives you a reference to the average in terms of the standard deviation. And really what it tells you is how many standard deviations above or below the mean a particular value is. Right, so if you were to get a standard score of 1, that would just say that this is a score that's exactly 1 standard deviation above the mean. If you got a standard score of -2, that would tell you that you're exactly 2 standard deviations below the mean. Okay, so standard scores can be positive or negative depending on whether the value is above or below the mean. So the formula here, it's a relatively straightforward one, is that the standard value will equal the actual value minus the mean divided by the standard deviation. And in notation, that gets written as x minus mu divided by sigma. All right, so let's have a look at example 2 here. We've got IQ scores, and IQ score is another example of something that a variable that's normally distributed. This question is saying that approximately 2.5% of IQ test scores are below 70, and 2.5% of IQ test scores are above 130. It's asking us to find the mean and the standard deviation for IQ test scores. Now, again, if you were to sketch your bell curve here to help you understand the question, what we would pick up is that, well, we don't know the mean, we know that's going to be somewhere in the middle, but we're being told two numbers where we've got 2.5% of IQ scores below one of these numbers and 2.5% above the other number. Now, if I think about 2.5% on the outside, that would leave me with 95% in the middle. And so really what we're saying here is I've got 2.5% above that, 2.5% below that, 95% in the middle. Well, that means that the two numbers I've got must be 2 standard deviations below the mean and 2 standard deviations above the mean, because that's the bell curve percentages that we know. And so we could say, well, if I mark that in as 70 and I mark that in as 130, and I know that a normal distribution has to be symmetric, well, then that's telling me a couple of things. One, it's telling me that the mean must be 100. So mean equals 100. And it's also telling me that if 130 is 2 standard deviations above the mean, well, that means each single standard deviation must be 15, because I've got 100, then 115, then 130. So the standard deviation is 15. Oops, sorry, that's part B, getting ahead of myself there. So what is the standard? Oh, no, I wasn't, just misreading my own question. Standard deviation is 15, that's an answer for part A. B says, what is the standardized score for a result of 91 on an IQ test? Okay, so the standard score, which we can shorten to Z, is equal to the actual value, 91, minus the mean, divided by the standard deviation, which is 15. Now, in most cases, these will be calculator questions, but not always, and this is one we can actually do without a calculator. We've got -9 on top over 15, which is really -3 over 5, which is fine to give that way, or we could say that's equal to -0.6. And what that's saying is that if you score 91 on an IQ test, you're actually 0.6 of a standard deviation below the mean. Okay, that's how we interpret that result. And we knew that that had to be a negative standard score because 91 is actually below the mean. Okay, last part of it, in a group of 50, approximately how many people would you expect to have an IQ greater than 115? All right, well, we could say greater than 115. 115 is 1 standard deviation above the mean, if we refer back to that little bell curve sketch there. All right, and when we have 1 standard deviation either side of the mean, we know there's 68% in the middle. And so above 115, that leaves us with the 16% when we use our bell curve percentages. What you're going to do with these questions, though, is read carefully. This is saying how many people. So in a group of 50, how many people, not what percentage. So the percentage of people who would have an IQ greater than 115 is 16%. But the answer isn't 16%, the answer is 16% of 50. So 16% of 50, which is 16 over 100 times 50, if you want something to chuck into your calculator. 16% of 50, which will give us 8 people. Okay, so 8 people in this group of 50 would be expected to have an IQ greater than 115. So with those questions, always read them carefully. Sometimes they're just going to be asking for the percentage, other time they're going to be asking for the number of things, the number of people, and so on. I might leave this exam question for another video because this one's already pretty long, but I hope that gives you a good idea of what's going on in 16B. And as always, ask your teacher if you need some help with anything. See you in the next video.